Greetings to all my tech heads out there in the KevTechify Nation, and if you're new here, welcome. In this episode, we're going to look at IPsec. We'll be discussing IPsec Technologies, IPsec Protocol Encapsulation, Confidentiality, Integrity, Authentication, and then finally, Secure Key Exchange with the Diffie-Hellman. This episode is part of my series on enterprise networking, security, and automation for the Cisco Certified Network Associate, also known as the CCNA. I'm Kevin here at KevTechify. Let's get this adventure started. The internet was not designed with security in mind. Back when the internet started, it was a private network. It was a very controlled environment. A handful of people or organizations were on there. They all trusted each other. It's not the beast that it is today. Today's beast, the internet, there's a lot of things going on out there. We have bad actors, we have viruses, we have all sorts of different things that can happen on the internet. When we look at security way back when, there was nothing there. Eventually, what we had to do was implement security at the higher levels. What we did was implement SSL and TLS, and that gave us secure web browsing and secure FTP. We also implemented SSH up here at the upper layers in the application layer here of your TCP/IP model. The network layer did not have any security, so we implemented it up at the higher levels. It was easier to do. Now, IPsec is designed to come in at the network layer. When it comes in at the network layer, we can use it for either IP version 4 or IP version 6, but because we're on this network layer, everything above it is secure. Now, when we say is secure, we mean that the transfer of the data is secure. Now, the applications still need to be designed securely. Your end users still need to be trained accordingly. But the transferring of the data here is secure because we are encrypting everything down here at the lower levels, making everything up here that deals with the transfer of data being secure. IPsec provides several things. First thing it provides here is the authentication. And what we're looking at here is data origin, data integrity, the protection against replay attacks. This is our authentication header. Authentication header, AH. IPsec also provides encryption for data confidentiality and keeping our data private, as well as authentication with integrity checks and protection against replay attacks. ESP, or encapsulating security payloads, will provide us with those things. IPsec also provides us with negotiation of security associations and keys through ISACAMP, IKE, and Diffie-Hellman. IPsec has two modes: transport mode or tunnel mode. Tunnel mode is what is used in VPN tunnels. IPsec can be implemented in the kernel of the operating system, or it can be added to the stack. Adding to the stack is more typical. We have the application layer, that is in software. The transport layer, that's TCP or UDP, that is also in software. Then we have the internet or network layer, that's IP, that also exists in software. And that was IP. IPsec is added here at the network layer, and that is also implemented at the software layer. In comparison to the network layer, where we have the data link layer and the physical layer, which is implemented here in hardware. When we put IPsec on an end device, we call that a bump in the stack. And when we add IPsec to a networking device, like a router, we call that a bump in the wire. So bump in the stack is that end device. Bump in the wire is how we travel through the network through those wires. Like a router, that's a bump in the wire. Here in this slide, we have the majority of protocols used in IPsec. IPsec is more of a suite of protocols than it is a set of technologies. Or AH, or once again, this was the authentication header, is more of a header than a standalone protocol. And it's declining in popularity, although it can provide the ability to authenticate data origin. That is, the data is where you think it's from, as well as the integrity of data, that it wasn't changed while en route. It doesn't provide confidentiality or encryption. Authentication header also doesn't work with NAT firewalls. It can't traverse network address translation. ESP, or once again, that was encapsulation, security, payload, does provide confidentiality through encryption, and it can provide some of the same authentication methods like integrity checks to be able to verify the integrity of the data. ESP is more prominent because of those reasons. Security associations, or known as SA, are used to set up basically a contract or a recipe for how your security is going to be handled from each device, each end of the IPsec connection or tunnel. Now, security associations are built on IKE. IKE is Internet Key Exchange. And IKE uses the policies set out in ISACamp to set up those security associations. Now, there's two phases in IPsec. They are the phase 1 in the security association and phase 2 in the security association. Phase 1 is used for management. Phase 2 is used for data. Phase 1 creates our policy set, and phase 2 creates our transform set. There's a single policy set, and there's two transform sets, one for inbound and one for outbound. Now, all of this that's set up in phase 1 and phase 2, these are basically all the security settings that we are going to be using. In phase 1, what's negotiated here for our policy set is the encryption or the confidentiality. So this is encryption here. And this would be typically either triple DES or AES. The hashing we would use, or the integrity checks, would be typically MD5 or SHA. And then we would also use HMAC in here, which is a key hash. Then the method of authenticating each end of the tunnel would either be with a pre-shared key or an RSA using an X.509 certificate. And then which Diffie-Hellman algorithm or group you're going to use to share those keys across the internet. Phase 2 initiates the transform set. They look at the different types of encryption and also hashing that happens. In the phase 2 here, this is used to secure our data. Those are the basic protocols or suite of protocols that you will see in IPsec. IPsec is an IETF standard, and what that does is defines how a VPN can be secured across our IP networks, how we can secure a VPN across public networks. What this provides us here is the confidentiality. We use encryption algorithms to prevent cyber criminals from reading the packet's contents. We get integrity by using hashing algorithms to ensure that our packets have not been altered between the source and destination. We get origin authentication using the Internet Key Exchange IPsec protocol to authenticate source and destination. And finally, we use Diffie-Hellman to do a secure key exchange. I hope you're liking this episode on IPsec. If you have the time, please leave a comment and let me know what you think about IPsec. You can also visit my website at KevTechify.com for all of my details and how to get these episodes in video and podcast form. For as technical as IPsec is, it's not bound by any specific rules for secure communications. IPsec can easily integrate new security technologies without updating existing IP standards. Here, we have for confidentiality, we have DES, triple DES, AES, SEAL. You could easily come up with another confidentiality encryption standard and use that here without having to go through and redesign this whole IPsec framework. When we look at this, a lot of times people think they describe it as we have open slots here in this IP framework. Shown here in this diagram, we have the IPsec framework, that gray stack of empty boxes. What you can do is go and pick what you want to place in there. Now, there are a couple things to pay attention to. If you pick this AH, remember, AH is not well used anymore. It's falling out of favor, and because there isn't encryption that you can choose with it. So a lot of times people don't choose AH here. A lot of times they choose our ESP, and so they'll put that into here. Then once we choose what protocol we're using, what encryption are we using? Now you should use triple DES, AES, or even if SEAL is available. Don't use DES. That's been proven to be unsecure, unreliable. So we can go ahead and pick our confidentiality. Now what are we going to do for integrity, our hashing, to make sure our data hasn't changed? You can pick either MD5 or the SHA. Go ahead and do that. Are we going to do PSK or RSA? Okay, let's say we're going to use RSA to set that up. Then which Diffie-Hellman group are you going to use? Now, word of advice here, Diffie-Hellman groups 1, 2, and 5. Yeah, don't use them. Once again, this is insecure. But we do have some higher ones and better groups. We're going to talk about that here in a second. Choosing an IPsec protocol encapsulation is one of the first building blocks you need to do. Now, IPsec encapsulates packet using either the authentication header, which is known as AH, or the encapsulation security protocol. You choose one or the other, and this is sort of the building blocks for everything else. Now, AH is appropriate, but it's only appropriate when confidentiality is not required. When you don't need to secure your data being sent. Basically, just don't use it. Most of the time in today's world, everybody's going to use the encapsulation security protocol. The confidentiality of our data, or encryption, so we have encryption here, is a method of encoding our data while in transit, so that way if somebody intercepts it, they can't read it. Now, Gail here is going to send Jeremy $100. Gail sets up the payment, sends it out, but before it goes out, it gets encrypted. And so it chooses an encryption algorithm. You can choose any of them, and then you apply a key to that. That key basically is what locks it and unlocks it using that algorithm. So we lock that data, we encrypt it. That data now, instead of saying pay to Jeremy $100, it looks like a string of random digits, letters, numbers, symbols. So if somebody on the internet intercepts that data, we call them threat actors. The threat actor gets that data, they're going to look at it and they're going to see all these random numbers and letters. They can't read that. And so that data travels across the internet, makes it to Jeremy, where he uses his decryption algorithm along with the key to unlock that data. When he unlocks that data, it decrypts it, it unscrambles it, and he gets his payment of $100 from Gail. To make it more difficult to decrypt your data, choose a longer key. The longer the key, the more possibilities there are to decrypt your data. When we're looking at our confidentiality, once again, confidentiality was our encryption. There are kind of four choices or four technologies that are used primarily on the internet nowadays. These are all symmetric keys. Now, what do we mean by symmetric? The same key is used to encrypt and decrypt the data. And there are advantages to each. Well, I guess I really shouldn't say advantages. The older technologies, the DES, it uses a 56-bit key length. It's the easiest, it's the least secure out of the other four out there. Then we have triple DES. What triple DES is basically 3 times DES. It does DES 3 times on it. It uses an independent key encryption. It does it 3 times. So that's more secure than DES. Then we have AES. They offer different key lengths here. The key lengths are 128, 192, and 256. Once again, the longer the key length, the harder it is to guess what the actual key is to decrypt the data. And then we have seal here. Now, you should use seal when available. Not everything supports seal. And what seal here is a stream cipher. That means it encrypts data continuously instead of encrypting blocks of data. And seal has a 160-bit key length. Because of how it encrypts the data, it is more secure than AES. When we look at integrity, integrity means that the data hasn't been changed while we're transferring from the source to the destination. We want to make sure that that data hasn't changed. There are 2 methods that we typically see used in today's networks. One is the MD5, Message Digest 5, and that's got a key length of 128 bits. It's a shared key. It's a shared secret key. And then there is the SHA. Most people consider the shared hash algorithm here more secure than the MD5. mainly because it's 160 bits long. But both of these make sure our data hasn't changed while in transit, the hashing of our data. There are two IPsec peer authentication methods, pre-shared keys and the RSA. Pre-shared key is a value that is entered into each peer manually. Now, it's easy to configure manually, but it doesn't scale well. You have to go to each client, enter that in, and if you got 10 clients, yeah, you just have to do it 10 times. But if you have 1,000 users, you have to go to 1,000 computers and enter that in. It must be configured on every peer you are setting up. Now, the Rivas, Shamir, and Alderman, or RSA for short, is an authentication that uses digital certificates to authenticate the peers. Now, each peer must authenticate its opposite peer before the tunnel is considered secure. But because you're using these secure or certificates, you don't have to go to each one. You can copy the computer, you can have it in your installation, you can have the user install these certificates. It doesn't take as much work from you. Also, the pre-shared key is considered less secure than the RSA method. Diffie-Hellman, or commonly known by its abbreviation of DH, allows two peers, so two devices that are trying to communicate each other, to share a secret key over an insecure channel. So over the internet, two peers could share a secret key. There are variations in the Diffie-Hellman key exchange, and they're specified in groups. And a lot of times you'll hear people talking about, well, we're using Diffie-Hellman 1, Diffie-Hellman 2. Now, there are some things to note about the different groups. Diffie-Hellman groups 1, 2, and 5 should no longer be used. These are considered insecure, so don't use them. Easily compromised in today's world. Diffie-Hellman groups 14, 15, and 16, they use a larger key from 2048 all the way up to 4096. Very long keys to encrypt their data. Diffie-Hellman groups 19, 20, 21, and 24, they have some key sizes, but their key sizes are a little bit smaller. They go from 256 up to 2048, but they use what we call the ECC method of encryption, which is the, let's see if I can write it in here, elliptical curve cryptography. ECC, the elliptical curve cryptography. Because it handles the Diffie-Hellman in a different method, we don't have to have as long as keys. Plus, it reduces the time needed to generate the keys. It's a lot quicker Diffie-Hellman group than the other ones. In transport mode, there's only a single IP version 4 header, which isn't changed. With protocol 50, because we are using ESP, we have an ESP header and an ESP trailer, and the ESP trailer tells us that the next header we're looking at is the TCP header that is here in the encrypted IP data. So once this is decrypted, we're going to have our TCP header. Here is the ESP authentication data. If this option is used with ESP, we're also going to have authentication, meaning we're going to have an integrity check. What we're going to do is we're going to hash all the way from the ESP header all the way to the ESP trailer. We're going to hash all of these fields so that we can verify the integrity of our data. Make sure it hasn't changed. Now, let's compare that to tunnel mode, which is used in VPN tunnels. In this case, the original IP version 4 packet is encapsulated and encrypted. Not only the IPv4 data with the TCP header and TCP data, including the application layer data, but including the IP version 4 original header is encrypted along with the ESP trailer. Notice the ESP trailer says that the next header it's pointing to is the header of the original IP version 4 packet. And then there is a new public IP version 4 header that was created. The new IP version 4 address points to the fact that we are using protocol 50, that we are using ESP, and we have our ESP header along with our ESP trailer and our ESP authentication data if we decide to have integrity checks. This is the type of packet you would see in an ESP or VPN tunnel, with the original IP version 4 address with the new public IP version 4 address. It was my pleasure to provide you with this wonderful episode on IPsec. If you like this episode and you got value out of it, and of course, depending upon what platform you're using, please click that like button, give a 5-star rating, leave a comment. This all helps me bring you more great content. Please take a minute to subscribe to my channel. All of my socials and contact information are on my website, KevTechify.com. There you can find out how to get all these episodes in video and podcast form. In the upper right is my playlist for my series on enterprise networking, security, and automation for the CCNA. In the bottom right is one of my favorite videos that I linked just for you. Thank you so much for watching this episode on my series of enterprise networking, security, and automation for the CCNA. Once again, I'm Kevin. This is KevTechify. I'll see you next time for another great adventure.